So far, we've used joules as the unit of energy. However, in atomic physics, which again is the physics of electrons, energies are so low that it's awkward to use joules. So a smaller unit of energy has been defined called the electron volt. Now be careful about the name. It's not voltage, it's not electrons, it's actually a unit of energy. Its value equals the potential energy of an electron in a region of space where the voltage is 1 volt. So we have this equation over here. The potential energy is equal to Q times V. Here's the charge on the electron. Here's 1 volt. And we come up with the conversion factor of 1 electron volt equals 1.6 times 10 to the minus 19th joules. When we're working with electrons, it's also convenient to convert Planck's constant to units of electron volt seconds rather than joule seconds. So here we have Planck's constant, 6.63 times 10 to the minus 34th joules seconds. We have 1 electron volt equals 1.6 times 10 to the minus 19th joules. The joules cancel out. And we're now left with H is 4.14 times 10 to the minus 15th electron volt seconds. And again, to summarize, 1 electron volt is 1.6 times 10 to the minus 19th joules. What's absolutely brilliant about Bohr's work is that his calculations, based on his assumptions, are in excellent agreement with the optical spectra showed earlier. So it is in excellent agreement with the experimental data. The next slide shows the various transitions between quantum levels, electron quantum levels, and they've been named for the physicists who first observed them. The Balmer series of orbital transitions are the only one in the visible spectrum, the only ones that can be seen with your eye. Here's how the spectrum of hydrogen look like when we take the various orbitals. We have n equals 1, that's the ground state. N equals 2 is the first excited state. Now we have the Lyman series that has electrons going from higher energy states down to the ground state. These are the highest energy transitions, and those are in the ultraviolet range. We next come to the Balmer series. These are higher energy orbitals decaying to the n equal 2, or the first excited state, and those in visible light. And then the Paschen series, that's when the higher orbitals decay to the n equals 3 state, and that's closer to the infrared range. And just to make the point again, Bohr's model exactly matched the observed spectra. And also the equations that were developed with the Rydberg constant. Those experimentally determined equations also match Bohr's solution.